We talk about AI like it's just this one thing, like it just exists.
Right.
But when you look at the research we've got for today, that's completely wrong. It turns out AI really has two very different lives.
It's almost like a Jekyll and Hyde situation. You really can't get the technology until you understand that split.
So today we're doing a deep dive into that life cycle, specifically how this massive, slow, power-hungry beast in a lab becomes that snappy assistant in your pocket.
It's the journey from learning the world to acting in it. And to do that, we have to rip apart the two core phases, training and inference.
Okay, let's start with training. Phase 1. This is the learning part.
Think of training as the semester of study. This
Yeah.
is the AI locked away in a library. It's just grinding through terabytes of data, trying to find patterns.
And adjusting its own settings, the
Yeah.
weights, to sort of make sense of it all.
Exactly. And the sources mention backpropagation here.
Which sounds intense, but it's really just checking the answer key, isn't it?
That is the perfect analogy. The model makes a guess, checks the answer, sees it got it wrong, and then it, tweaks its own wiring to get closer next time.
And it does this millions of times.
Millions. It's incredibly expensive computationally, takes weeks, sometimes months. It's a huge energy drain.
But it has time. It's a student. It can pull an all-nighter if it needs to.
But then you graduate, and that's phase 2, inference. The sources call this the final exam.
And suddenly all the rules just change.
Completely. In inference, you take that trained model and you freeze it. No more learning. No more answer keys.
Right.
The model now has to look at brand new data, your voice command, a picture, whatever, and make a prediction instantly.
And there's a ticking clock.
Speed is survival. If the student hesitates on the exam, they fail. And these two phases, they happen in totally different worlds. Training is inside the lab.
Where you have the supercomputers using what the slides call 32-bit floating point math.
Which is just a way of saying super precise numbers. Think tons of decimal places. It's heavy work.
But you can't afford that out in the wild.
No way. During inference, you're usually running on the edge.
On my actual device. My phone, a camera.
Exactly. The parameters are frozen. It's not learning anymore. It's just doing. And because you're on a device with a little battery, you get a new enemy. Latency.
The delay. That gap between asking the question and getting the answer.
Yeah, and the notes are pretty blunt here. In inference, thinking too long looks like freezing.
If you ask your phone something and it just hangs, you assume it's broken.
We actually have some data on this. A comparison between a standard model, BERT, and a streamlined one called DistillBERT.
And the difference is pretty stark.
It is. The big BERT model was 87% accurate, but it took 54 milliseconds to respond.
Which doesn't sound like a lot, but it feels like an eternity.
It does. Now, DistillBERT, it dropped accuracy by just 1% to 86%, but it cut the latency in half, 27 milliseconds.
So you trade a tiny bit of brain power for double the speed? How do they actually do that? You mentioned that heavy 32-bit math.
They use a technique called quantization. It sounds complex, but it's basically rounding. Instead of using those heavy, precise 32-bit numbers, they compress them down to simpler 8-bit integers.
Ah, so it's like taking a huge high-res photo and saving it as a JPEG so it loads faster.
Perfect analogy. You make the model about 70% smaller, much faster, but it leads to the big question. Is that trade-off really worth it?
A 3x speed increase for a 1% drop in accuracy.
Is it worth it?
Well, the case study here is Face ID on a phone. That seems like a clear yes.
It is. You look at your phone, you need it to unlock now. You don't want your face data being sent to a cloud server. That's a privacy nightmare, and it's slow.
So it all runs locally on the device's neural engine.
Edge inference, zero latency, total privacy, no data costs. And if it fails once in a while, that 1% drop, you just look at it again. The consequence is minor annoyance.
But wait, annoyance isn't always the worst-case scenario. What about when accuracy is everything?
That's where we refuse to compromise. Think about medical diagnosis. An AI is scanning an MRI for a tumor. Do you care if it takes 50 milliseconds or 5 seconds?
I want it to take all day if it means it gets it right.
Exactly. In high-stakes medicine, we do not quantize. We keep the heavy 32-bit math. A 1% error there is catastrophic. We tolerate the latency.
But then you flip it to the other extreme, like autonomous driving.
Or high-frequency trading. There, speed is survival. Again, if a car sees a shadow that might be a person, it can't spend half a second analyzing it perfectly. It has to break now.
A 95% confident decision made instantly is better than a 100% decision made too late.
A half second too late is a crash.
Wow. That's a wild balancing act. So to zoom out, these two phases, they form a loop, right? Training and inference.
They do. It's the cycle of intelligence.
Right.
Training builds the brain, inference uses it. But here's the kicker. The data we generate during inference, all our real-world use, is what gets fed back to train the next generation of models.
Which brings up a kind of a spooky final thought to leave everyone with.
Go on.
If our future AI is being trained on data that was generated by our current AI, are we creating a closed loop, a kind of synthetic reality?
That is the billion-dollar question. If the snake starts eating its own tail, does it get smarter, or does its world just get smaller and smaller?
Something to think about next time your phone unlocks in a millisecond. Thanks for listening to The Deep Dive.